Good afternoon, everyone, and it's my pleasure to be here at the ACI convention in Baltimore. Thank you to Cesar and Mario for organizing this session. So with all due, let me go forward. Let me see how it works. There we go. So I'm just going to give you a presentation about low damage precast concrete bridges. And let me start with an introduction, just a single question, and is really in the way we design our codes, are we really addressing the issue of the society call for resilience? And the answer is maybe no. We still keep doing the same things with some differences to what we were doing in the 1970s. We don't think too much about functional recovery. How are we going to get back into business or so? So let's go back to history and see how do we begin. In the 1970s, or in the 60s, we knew about energy dissipation and about ductility, but we didn't know how to put it together. So we had the 1971 earthquake in San Fernando with significant damage to the bridge infrastructure. Were connection failures, shear failures, just about everything. Then in the 1970s, there was a new way of thinking in New Zealand stemming from the plastic design coming from Europe, where we could select a mechanism, kinematically admissible mechanism, and design for seismic to form plastic hinges and make those plastic hinges to have enough ductility so they could deform plastically, admitting that there was going to be some damage. So this image is from a booklet that Professor Park and Professor Pauly prepared back in 1992. So then what they say, look, if we have the potential for a mechanism, there could be many mechanisms that can develop. So via capacity design, they say you just choose the mechanism you want. One of the mechanisms you prefer, going from the top ones that are the preferred mechanism, and the bottom ones that are the least desirable mechanisms where practically you want to avoid. And then there was the development of capacity design. In capacity design, just not to go through the lines or so, you basically have, here is the Tom Pauly's chain analogy. You have a ductile link and a brittle link. And depending on the interplay of the strengths, you can have your system being ductile or brittle. So if you have the brittle link, which is weaker than the ductile link, you still have a system that is brittle. But if you have a link that is not only ductile, but is also not as strong as the brittle link, you have a ductile response. So there we initiated the design of bridges for ductile response, where were very common in New Zealand up until then, or from the 1980s, and in California from the 1990s after damage to bridges in the 1987, 1990, 1989, and 1994 earthquakes. There was a call for a test to see if the confinement levels in ductile bridges will work. So we did this in combination with Caltrans, UC San Diego, where I used to be a professor, and the University of Nevada, Reno, UC Berkeley, and we tested on the shaking table a full-scale bridge column that was well-detailed for ductility. And that's what we see. Let's see, yes. So you can see the bridge there, you can see the hysteretic response. I'm not going to go through every figure here, but you can see a good hysteretic response. And it seems that everything is working just fine. If we look at the drift ratio here, or the plastic hinge rotation being similar to the drift ratio in this test, we attain about 6%, 0.06 radians. It's quite a bit, actually. And what do we see? Well, we see similar things that are good for capacity design. The pros is the advantage is that we can design something that is ductile. It can dissipate energy, it can deform significantly, but at the expense of damage. So things that we observed in these tests were observed also by Professor Alessandro Palermo in the Kaikoura earthquake in New Zealand. Yeah, you do develop a plastic hinge, but in the end, your bars tend to buckle and fracture. And that is the question of functional recovery. How long will it take if I can repair this column? So yes, we are now able to save lives because the bridges are not collapsing, but now we are moving forward into society as asking you questions. Can we really go back or not? And this is the case in the column that we tested in San Diego. You can see one of the reinforcing bars, and you can see actually the bar, when it buckles, it develops a crack at the root of the bar deformation, maybe where you least expect to see that crack. Because if we think in engineering terms, we think that there should be compression there. But if you think in engineering mechanics terms, there is actually a lot of shear deformations in that region, a lot of distortion, because the bar deformation itself is quite imperfect when you roll the bars. So they act as crack initiators. And here we go. This is a video of, let me see if yeah. This is the column that we just tested. And they fracture. And these bars are what we call number 11 bars. These are big guys, not small ones. Can we repair those columns? Maybe yes, but it will take some time. So very interesting concepts were developed in New Zealand back in the 1970s by Dr. Ivan Skinner, who, by the way, was not a civil engineer. He was an electrical engineer who developed base isolation. But he was also thinking in many other devices, and among all the devices they developed was this with Professor Jim Beck from Caltech, who was a professor at Caltech. And this is a stepping bridge. A stepping bridge is one that can actually articulate, dissipate energy, and come back. So the advantages of this is that you have no plastic hinges, you have no damage, and in the worst case scenario, you can remove and change the hysteretic devices, similar to the C shape you just showed, right? All these concepts were basically proposed by Dr. Skinner, right? But the disadvantage of, let me go back, the disadvantage of this specific bridge is that it requires a specific geometry to uplift and go back, because you are just playing with the mass of the bridge. So for some configurations, it won't work. So it is a good idea, but it's not applicable to everything else. So what happens is that you go into post-tension bridges, like take this step further, and that's what Professor Nigel Priestley and his group developed through the PRESS program, right? We were working in parallel with him in New Zealand, working on post-tension columns. And we see that those applications or those type of concepts themselves, where you are post-tension in a column, are also applicable to bridge columns themselves. So in a way, you have an articulated toy here that you push and pull, and you push and pull, and it goes back and forth. So you have a nonlinear elastic response. And you can have it this way in a cantilever wall or bridge column, where you just push and you develop a nonlinear elastic response. You return back the same way, and everything is good. You have no damage, right? It recenters, so it's something that you want to see after an earthquake, that, hey, I have gone through a large displacement, I have no damage, it recenter. Therefore, I mean, that is the concept of resilience, zero downtime. And Only the big problem is that there is no large energy dissipation in this system, only through impact or so. And the demand on these systems is incredibly highly variable. So sometimes it works, sometimes it doesn't work. What we can do is add a little bit of energy dissipation, and that can be through metallic devices, or some other colleagues have worked in viscose devices or so. So in this case, we work with metallic devices. We just push the same way. And when the pre-stressing tendon is forcing the column to go back to zero, the energy dissipation devices yield back and dissipate energy. And that's what I want to concentrate a little bit the rest of the talk. There is no damage. There is energy dissipated through the hysteretic devices, recenters, yeah, and the response is predictable. If you have sufficient energy dissipation, your response is actually quite predictable. We can argue that it costs a little bit more. The initial cost could be a little bit higher, but if you look at the complete cycle, maybe that's not the case. So we had the opportunity to work on those bridge systems. They were called here work funded by NCHRP, which is the research arm of ASH2. And we were working here what we call is a dual shell column, that we have a steel shell on the outside and a steel shell in the inside. And those steel shells act as formwork. They act as shear reinforcement, as anti-buckling reinforcement, and as confinement reinforcement. And you only have the gap opening at certain locations in the bridge, in this case at the base of the column. So it's the same concept. We're just going to exercise the column. The only thing in this case is that it will require some kind of bedding mortar to be able to open and close that gap. So that could be the Achilles tendon in this case. So we can actually say, well, what do we want to have? We want the gap to close and the column to recenter. We want to have energy dissipation. We want to have linear response of the pre-stressing tendon. If they yield, we lost it, right? So we want to ensure that the device that is going to dissipate energy is going to has enough ductility and toughness to take the number of cycles that is going to undergo. And obviously, our last one here, the design of the rocking interface, is very critical one, and I will show you why is that. So I'm not going to go through equations here. We need two criteria here. One is ensure that the gap closes, and the second one is ensure that we do have at least a minimum amount of energy dissipation where we can have some predictability in the response. You have to meet both criteria to do that. And graphically, we can put them in a little clock like this. The lambda c at the top goes basically from 0.01 to infinity, and lambda d goes from 0 to 1. And depending on where you put those arrows, you get a different, some kind of hysteretic response. If you have at the extreme, you have actually no energy dissipation, is what we have here. It's a rocking body. And at the other extreme, you have a conventional bridge column where you are dissipating energy and you don't recenter. You have a permanent deformation. So somewhere in between in that domain, you actually have systems that will go and recenter, like this one. So the other criteria is that you want to keep that tendon, those tendons, within the elastic range. You don't want to yield them, because the moment you yield, you lose the capacity to recenter in the column. So those are for the energy dissipators. You want to maintain. You don't want to go all the way to, if you are using reinforcing bars, you don't want to go all the way to the uniform strain of the reinforcing steel. You want to keep that strain in a reasonable range, say 3 or 4% maximum. You can do many, many tests back and forth, tension and compression, as long as you prevent them from buckling. So everything is theory, everything is beautiful, all equations, but guys, if the experiment shows that it's not okay, we better acknowledge that, right? So doesn't matter how beautiful the theory is, but if it doesn't measure up in a test, that's it. It won't work. And sometimes we just go too crazy with the theory and forget about the experimental work. Okay, so we tested, came up with a column here. Our colleagues, Gabriele Guerini, who is at Pavia these days, and colleagues from Berkeley, collaborated with colleagues from University of Washington and again from Nevada, Reno, and came up with the same concept of the dual shell column. So it's full of concrete in the inside, and we make that column as short as possible to see the shear transfer. Everything looked like perfect to, what is this? Let me go here. So we looked at the numbers in our little clock, and we expected a response like this one I show here. We put any dissipators in the way of mini BRBs on the outside. Those were actually developed initially by Professor Palermo and Pampanin at Canterbury University, and very kindly they shared with us their ideas. We provided a joint with high performance grout or bedding mortar. So no, we didn't see any problem at all. Now, we did the test, and I could sell you the idea, or try to sell you the idea that the performance was actually pretty good. But the reality is that it wasn't, because that mortar joint began to crash. And as it crashed, the column begins to shorten. And as it begins to shorten, you lose the pre-stressing. So it's like we are not there yet. So we had to do something different. And what we came about is we are not going to try to solve the problem. We are trying to avoid that problem. And by doing that, we are not going to have the interface with a bedding mortar. We precast the entire column, including the joint at the top, including the joint at the bottom, inside a tube that has joints at the top and at the bottom. So we cut that tube at the top and at the bottom to allow the rocking interface to occur, right? And that way we had the contact of the rocking surfaces all with cast-in-place concrete. This is the fabrication. You see some ribs, because in this case, we basically want the column, the shell to work as a composite. Again, if we throw the clock numbers, we're going to have recentering response. This is the construction. We had a two-column bend. We placed the columns in sockets at the top and at the bottom, grouted those sockets. And this is a shaking table test at UC Berkeley shaking table. In this test, we have vertical and horizontal input. And you can see the little dot there. After the test, the column is recentering right there. So, and here we are going to fairly large displacements as well. This is a close-up at the base of the column. No problems there. And this is a series of tests that we did. So if we look at the number of tests that we did, can we really do those numbers of tests without damage? Some of them, 3 of them attain about 7% of 0.07 radians. in the rotation of those hinges, which is actually pretty huge, with no problem in the test. No linear model, this is actually not difficult. It's much easier than you have bedding mortar. Because when you have bedding mortar and crushing, it's actually not straightforward to model that region. But if you avoid the bedding mortar, modeling these type of columns is actually pretty straightforward. There you see the test and the pre-test and the post-test prediction. The pre-test prediction is actually excellent compared to what we expect. Usually we have the prediction that we do is actually not very good always. We always call it prediction after the test, which should be a post-diction or so. But in this case, actually the prediction was very, very good. We did the post-diction as well to improve it, but there was not much room to improve there. With that, how many minutes do I have? 2 minutes, that's pretty good. So basically, we are going through an exciting period in the field of seismic design with these low damage bridge columns, or in general, low damage bridges or port structures or whatever you want to do, buildings or so, where you actually conceive a structure that will articulate and without having any damage, which means right off the bat, we have a resilient building. The functional recovery 0 time or so is there. And basically using very basic concepts of unbonded pre-stressing, we can build these buildings precast and tension them in a very easy way, put them together, and it's done. It's very, very simple. That's all, and be happy to answer questions. Thank you very much.